once again, and welcome to MEL Science. Delight and a pleasure to have you here. I'm just going to change my screen so I can see everybody. Gallery, where we're going, so I can see. Aha! So we just to sort of make it a little bit sort of personal. I'm glad to see that some of you switched your screens on. So who we've got? We've got John Davola. Hello, John. Taylor. Hello, Taylor. The Stotts are there. Simon, Kelly. Skelly Schoolfield, lovely name, very appropriate, highly appropriate for our science program here. Daniel, cracking name. I can't hardly recommend it too highly. Anna, Estas, Evan, Juan, Elizabeth, and Abby. Hello to you all. And Taylor. Hello, Taylor. Yes, Taylor's got a hand up. Taylor, you missed to. Hi, Anna. Hi, Abby. Hello. Everyone's got the screens on today. Shockingly friendly crowd this afternoon. Taylor, hi, Taylor.
My name's actually Vance.
Hi. Vance, I shall try and remember that, Vance. Thank you. I've written that down.
I'm just using my stepmother's computer.
Fantastic. With her permission, I hope. Okay, cool. Excellent. Right. Lovely to have you all on board and ready to do a bit of chemistry. So what are we doing? We are doing, hopefully, the show is about diffusion. Does that sound as though it rings a chord with everybody? Yes, it sounds as though it rings a chord with everybody. Okay, cool. You can, if you want to ask questions at any point, please just put up your hand and ask a question. It is your show. It is your science session, for example. So without much cracking ado, we'll get down to what we need to do today. So today, with diffusion, you need definitely a potato, access to a potato. Please make sure you have a potato. You also need access to some hot water, some boiling water. So I've got a flask here. So you need access to that boiling water. You also need access to some just normal tap water, room temperature tap water. And then the diffusion kit. So today we're going to be doing 3 wonderful diffusion experiments. And I'm also then going to explain some of the science and the chemistry, obviously clearly behind it for you. So we're going to do diffusion through plastics. We're going to do detective iodine. And then we're going to go and do through chemical reefs. So chemical reefs, really beautiful to sort of diffusion practicals. So the equipment that you need from the kits are, in no particular order, just check that you have all the chemicals. Start with the chemicals. You need potassium iodide. So please check that you've got potassium iodide. You need the copper sulfate crystals. You need the sodium carbonate. We need the iron alum. You also need the potassium hexacyanoferrate, that yellow labeled. And again, some more copper sulfate is the second tube. You need your syringe, some earbuds, some filter paper, the little plastic bag. We need the plastic bag to start with. And I'm going to do the experiments in specific order because they take a little bit of time. Some of them take slightly longer than others. You need some little stirrers. You need 2 little cups, plastic cups from your starter kit. Some Petri dishes. Vance, I'll get to you in 3 seconds. Give me 3 seconds. Some Petri dishes and your glass beaker from the starter kit and a grater and a knife. Okay, and gloves and glasses. So gloves and glasses. Okay, cool. Vance, yes, us on mute. Hi, Vance. Go for it.
I do not have a potato. Is there anything else that I can use?
Yes. Have you got some flour?
Like baking flour?
Yeah, like sort of bread baking flour, yeah.
Yeah.
Or some rice, yeah, some rice or some flour, something of that nature, yeah.
Okay.
Yeah, that would.
Thank you.
You're very welcome. It's a pleasure. Okay, is that another little hand up? Daniel, have you got a hand up? You haven't? Okay, just checking. It looked like you had a hand up. Okay, cool. Right, without much further ado, then what we're going to do is I'm just going to move all the stuff aside. We're going to start with the diffusion through plastics. Okay, so diffusion through plastics. So for that, we will need, for those of you who have a potato. The chemicals you need are potassium iodide and copper sulfate. So potassium iodide and copper sulfate. You also need your little tray. You will need your glass beaker. So have your glass beaker. And this is where you also need your hot water. So the hot water. So first things first. What we need to do, of course, is get our gloves on. Now, I haven't got any gloves, but if you have got your gloves on, grab your gloves. I can see lots of gloves being worn by everybody. Simon, fantastic. Avius, Vance, the Stotts have got their gloves on. It's come equipped. Awesome. And Abby and Evan and Kelly. Excellent. And Shingan. Oh, hi, Shingan. I didn't see you clip in there. Welcome. Lovely to have you. Right, I'll just quickly put their gloves. Oh, and what I haven't done, of course, everybody, is put the chat on. So let me just get the chat up and so I can see that. Okay, and at the end of this as well, if you would like a little postcard, just to recap on what you've done in this thing, all you've got to do is put a little postcard request into the chat, and we'll get you one of those little postcards sent off at the end of the session. So here, I've got my gloves on, I've got glasses on, so let's crack on. Right, so first things first, what you need to do is get your potato. Now I'm going to chop my little potato in half, and we're going to get some slices of the potato. So this is a source of starch, okay? So a source of starch. So I'm just going to get my potato here and grate. So produce some gratings of the potato. You don't need very much, probably about sort of 2 to 3 tablespoons. So some gratings of the potato. Or a little bit more than that, Dan. Okay. So grate away. Grate, grate, grate. Watch your fingers on the grater, of course, because little bits of fingertips don't really count in this experiment. So grate, grate, grate. Yes, as I said, you want about a tablespoon of that. That will do just fine, just fine. So pop that away. Okay, so once you've got your gratings, your little bit of potato gratings, okay, you need to push these into your glass beaker. So pop those into your glass beaker, like so. So as I said, potato is a source of starch. And iodine, I'm going to give my mat a little wipe, and iodine reacts with starch to form what's called a clathrate, which is, in this case, going to be a black substance, okay? Right, there we are. And I will explain all of that very shortly. Okay, so into our beaker, what we want to do is put 100 mils of boiling water, okay? So put 100 mils of boiling water into our beaker. Whoops. So 100 mils of boiling water into our beaker. That is going to help the starch extract some of the starch. We're going to create effectively a starchy solution, okay? Starch isn't massively soluble, but in a bit of hot water, it'll help it come out of the cells and create a starchy solution. So just give that a little stir. Just give that a little stir. Okay. Everybody okay so far? Yeah. No, we're not waiting. I'll get away. Yeah, I've got one thumb up. I've got one thumb up, so I just have to wait a little bit for you guys and girls. Sorry. Yeah, I've got 2 thumbs up. So we just wait till we get a couple more thumbs. Nice one. Nice one, Vance. Excellent. Cool, cool, cool. Vance, I take it you're using the flour, yeah? Yeah, perfect. That's great. That's perfectly fine. Perfectly fine. Okay, cool. So giving it all a stir. I think we're all ready. I can see lots of stirring and I can see lots of starchy solutions, which is great. Okay, cool. So once you've got that, and just put that to one side, what we need to do now is create the reaction vessel itself. So if you put a little cup, so get a little tiny plastic cup from your starter kit. Okay, so a little starter cup from your starter kit. I'm going to move that up a little bit like that. And open up the little bag. So open up one little bag and put that into the cup, like so. So open up the little cup. Now, with your spoon, you want 2 big scoops of the potassium iodide. Now remember that there's a little safety seal in the potassium iodide, so you'll need to depress the safety seal, look. So push that down, like so. Okay, and now you want 2 big scoops of the potassium iodide into your bag. So 2 big scoops into the bag. So that is 1 and 2. So 2 big scoops of potassium iodide. And of course, that is the chemical where the iodine is present. And you can see that solution is pretty colorless. Okay, so it's pretty colorless. Now what we want is 1 big scoop of the copper sulfate. So here, 1 big scoop of the copper sulfate. Okay, so 1 big scoop of the copper sulfate. And then something rather remarkable happens when you put that copper sulfate powder into the solution. Okay, so pop that into the solution and seal it up. Seal up the bag. So seal up the bag. Okay, give that a little workaround, a little tiny shake about, and it's got a very strange color. So you can actually see now iodine. And then put the whole bag into the solution like that. So put the whole bag into the solution like so. Okay, so you're sitting that bag into your starchy solution. So you're sitting that bag into the starchy solution. Okay. Now, that whole thing is going to take about 10 to 15 minutes to cook. Okay, so 10 to 15 minutes to cook. And so I'm going to leave that a while. I'm going to come back to it. I'm going to go through some slides and show you a little bit of the science. But hang on. Now, somewhere around the world, everyone's got some iodine solution. So this is a very messy bottle look of iodine solution. Okay. Now, what I'm going to do, see, this is iodine solution, and I'm going to put it directly onto the potato and just see what color it goes. Okay, I'm going to put this directly on the potato and see what color it goes. So this is just a demonstration for you guys. Okay, but watch. Look, if I put this on the potato, can you see what color it's going? Can you see what color it's going? Yeah, it's going a black color, isn't it? Yeah, everybody can see that? It's going a kind of black color. Okay, that's iodine directly in contact. Now remember this, that's iodine directly in contact with starch, okay? Directly in contact with starch. I'll just put that to one side. And we'll come back to that a little bit later. Okay, cool. Right, let's just go to a couple of slides and explain a couple of things before we crack on to the second one. So it's all about diffusion, okay? So what does diffusion actually mean? Well, it actually comes from the Latin word diffusionem, which means to spread out. Okay, so that's what diffusion actually means. Diffusionem. And you can actually impress your people, your friends, with the Latin and the Italian sound, of course, of a little bit of Latin. Okay, now we have it. Diffusion's all around us, of course. And I think a lot of you guys and girls who come from America, you will often have seen a skunk. What happens to skunk? How do you know a skunk is in the neighborhood? Yes, it smells, because those particles of skunk juice have moved through the air. They've diffused through the air. These molecules move through the air. And also, if you eat these Brussels sprouts, why are they a bit antisocial? Why are they a bit antisocial? I've got a hand up. Got a quick hand up. Vance, go for it. Asked to unmute. Vance. Hi, Vance. Asked to, yes. Oh, copper sulfate. 1 scoop of copper sulfate crystals as well. And then seal up the bag. I've got a hand up. Yes. Hello. So why are Brussels sprouts slightly antisocial? A hand up. Abby. Hi, Abby. Asked to unmute. Hi, Abby. Hi, Abby. Sorry, you're muted again. Yes, go for it.
So, Brussels sprouts, they don't smell very good when they're cooked.
You're right. They don't smell so good when they're cooked. But when you eat them, what happens to people sometimes when they eat them? You get a little bit of gas, and that gas isn't so nice either, okay? You get that special sprouty Brussels gas smell, okay? And that diffuses as well, and that produces the gas. The gas that stinks is called hydrogen sulfide, and that little molecule travels really quickly, okay? It diffuses really, really super quickly. Okay, so I'm just going to pop it on that, and then we're going to start the next experiment and then come back to a bit of the science. Okay, right, where are we going to go to next? So the next experiment we're going to do, okay, and I said we'll come back to this potato one very shortly, but the next one we're going to do, look, is detective iodine. Okay, so detective iodine. So what do we need for that one? Okay, so for detective iodine, now this way you're going to have to take your gloves off in a minute, okay? So detective iodine, once again, you need 1 big scoop. Okay, so you get one little cup, and you need 1 big scoop of the copper sulfate. So you get your copper sulfate and 1 big scoop, okay? 1 big scoop of that into the cup. So 1 big scoop of that. Then again, we need 2 scoops of the potassium iodide. So 2 scoops of the potassium iodide. So 1 big scoop in the cup, and then 2 scoops of the potassium iodide. So 2 scoops of that potassium iodide. Now this is where you need your little sweaty fingers, okay? So this is where you need your little fingers. So just give that cup a little bit of a swirl around. So just give it a little swirl. Okay, a little swirl. And we've got a little bit of iodine coming out of there. So what you've got to do, look, is get the card. So get one of these little cards and put 3, press hard. Hi, Vance. Vance! Asked on mute. Hi, Vance. Go for it.
Can you please slow it down a little bit?
Yeah, sure, Vance. Yeah, no problem at all. No problem at all. So in your cup, look, you got copper sulfate and you've got potassium iodide. 1 scoop of the copper sulfate and 2 of the potassium iodide. Now, with your paper, put 3 fingers and press hard into the center of the 3. Oh, press down hard on the paper. So your fingers are covered in fat and oils, okay? It's actually called sebum, okay? And so press hard with your fingers, your ungloved fingers like that, down onto the card. Now, this is the trick here. You turn the card over and put it on top of the little cup here so that the area where you had your fingers is now going to be exposed to what's ever in the cup, okay? So I press down hard here, look, and you can't see anything here at the moment. But then you press that down there like so and just leave that be. We need to leave that for about 10 to 15 minutes, okay? So just leave that for about 10 to 15 minutes. So what's actually happening there is the potassium iodide is reacting with the copper sulfate to release a funny, mysterious gas, and it's iodine vapor gas, okay? You know, when you go to a swimming pool, what's one of the chemicals you can smell in a swimming pool? Anybody know? Anybody know what one of the chemicals is they put in a swimming pool? Aha, got a hand up. The Stots. Hello, Stots. Go for it. I'll stop mute.
Hold on. Okay, go ahead.
Chlorine, that's what you smell.
That's exactly right. It's exactly right. Chlorine. Fantastic. Now, chlorine belongs in the same group as iodine, that brown chemical that you can see. And if you see here, the group is called group 7, and it starts with fluorine, and you've got chlorine, and then you've got bromine, and then our little friend iodine that we're playing with at the moment, okay? And they're all part of what's called halogens in the periodic table, okay? They're called halogens. And iodine's right down the bottom, so it's in the same group, okay? It's much nicer halogen. They're all pretty harmful, but iodine's a lot nicer than the rest of them. Okay. Now, just a quick look at the slides, more return to the slides, and then we'll come back to the last experiment. Okay, let's crack on. And of course, the whole why is diffusion important? Why do we even mention it? It's because the perfume industry alone, for example, is a multi-billion-dollar industry where scientists like you, young scientists, are basically trying to design a chemical that will go from you or somebody else to you or somebody else really quickly. There's no point in designing a wonderful smell that doesn't move very fast. You want a wonderful smell that moves really quickly. Okay, so diffusion is very important for perfumes, for example. And it's all about particles. Now, I'm sure you're all aware of atoms and molecules. Yeah? Yeah, kind of everything's made up of atoms and molecules. Kinda. There was a bit of shaking of heads there. Okay. Just to recap for those who don't know, okay. So everything's made up of little tiny particles called atoms and molecules. And so you know that air has got oxygen and nitrogen, stuff like that. Those are molecules, and they fly around all over the place at high speeds, okay. And you get diffusion in tea. So for example, if you put a sugar cube into some hot water or something like that, you know that eventually all of that water will become sweet eventually, okay, even if you didn't stir it, because it diffuses around. And also in our cells, when we breathe, we've got some oxygen. The oxygen's going into your lungs and through your cell walls and into your body, okay? And that all requires diffusion as well. And I'll come on to the who's who and the scientists of diffusion in a moment. So let's start experiment number 3. Okay, so experiment number 3, and then we'll come back and visit them all, okay? I'll come back and visit them all because they're sort of cooking at different rates, okay, different rates. Okay, so I'm just going to put that one to one side. And now what we're going to do is really beautiful chemical reefs. So chemical reefs. Is everybody with me so far? Yes. Oh, lovely, perfect. Yes, nice one. Lovely, AV. Yep, fantastic, AV. Thanks, Vance. And the Stotts are there, and Simon and Evan's looking very quiet. Kelly, you okay? And Abby, yep, we're all good. Lovely. So chemical reefs. So what do we need for that one? So first of all, if you get some filter paper, so a little tiny piece of filter paper, Okay, and put the filter paper there like so. And now what you want is the small Petri dish. So the little tiny small Petri dish, and put that on there like that. So small Petri dish. This is where you want the cold water. So I said access to, aha, got a hand. Avi, hi Avi. Asked to unmute. Hi Avi. Go for it.
It's actually Avi.
Oh, sorry Avi, sorry, I'm so sorry. Yeah, how can I help?
No, I'm just telling you.
Oh, right, you're just correcting my pouring. So I'm so sorry Avi. Yes, gotcha, I've got you. Okay, so take 10 mils of cold water. So take 10 mils, so I'm not really showing you that very well. So take 10 mils of cold water, 10 mils with your syringe, and pop that into the little Petri dish. So pop that into the little Petri dish, okay? Pop that into the little Petri dish. Now, the next thing you need to do is get your copper sulfate again. So here's the copper sulfate. So copper sulfate, the red or the blue one doesn't make any difference. It's the same substance, so red or blue. So that's the copper sulfate, and you also need the potassium hexacyanoferrate. So potassium hexacyanoferrate. So those two chemicals, okay? And you also then need 2 of the cotton buds. So 2 little cotton buds like so. Okay, now what you need to do with the 2 cotton buds, hopefully everybody's got that. What you need to do with the 2 cotton buds, look, is just wet them a little bit with that water. So just wet them a little bit, just pop them into the water, just wet them, okay? And now what you need to do is we're going to dip them that wet. You know, like you've done before, I'm sure with your finger was a bit sort of wet, and you stick it in the sugar bowl, and you get the sugar stuck to the end of your wet finger. Okay, what we need to do, look, is get the potassium hexacyanoferrate. So potassium hexacyanoferrate, and just pop it into the bottle like this, the wet end, and get a little clump of it. Look, see a little clump of the crystals are stuck to the end of that, and pop that into one side of the Petri dish very carefully like that. Just dump them in there like that. And then you repeat that exercise with the copper sulfate. Repeat that with the copper sulfate on the other side. So this is the copper sulfate. And then look, repeat that on the other side. So there, like so. Just going to make sure that's all on there. And then something strange and magical should appear very gently in the center between those 2 little piles of chemicals. Something very gentle should start to appear in around about 1 to 5 minutes. Okay, so around about 1 to 5 minutes. Something very gentle and really rather beautiful will start to appear. So just wait for a second or two. Okay, just wait for a second or two. Aha, Vance, got a hand up. Asked to mute. Hi, Vance.
Is it like a crimson red?
Yeah, it might. Yes, it starts to form a little tiny reef. That's why it's called the reef. Okay, the sort of crimson reef. But it should slightly go like a browny reddish sort of color. Yeah, it should start to form. Don't move it. Don't shake it because it's very, very, very gentle. Okay, right. Now, what we can do, just quickly, just a couple more sort of slides to wick through some of the little history about diffusion. Then we're going to come back to our fingerprints, detective iodine. And then we're going to come back to our potato. Okay. Right, quick slideshow. Okay, so who's who? Who are the scientists behind diffusion? And what does it all mean? And what do they do? Okay, so the first one really is this chap called Thomas Graham. He was the first person to study the behavior of gases, that gases were actually things that moved around, okay? It's amazing that he only started doing that in about the 1850s. It's quite funny, isn't it? We've known for years and years and years that funny smells waft through the air, but he was the first person to really study what is it that's moving through the air and how do we detect that, okay? The next person is a guy called Adolf Fick, who comes across Fick's law, and he's the first person to say that substances go from a place of high concentration to low concentration. And again, this is only being done in the 1850s. So it's literally only 150, 200 years ago that any of this science was actually being done. So it's actually kind of fairly new. Okay? Then we have the great James Clerk Maxwell, who told us how gas particles actually move, and he had kinetic theory of gas. Because remember, around you, gas particles are moving all over the place, but he was the person who really formulated the first law of how gases move. And then we have Ludwig Boltzmann, who came up with the second law of thermodynamics, which underpins practically everything in life. And now don't worry about that, you don't know the names or the terms, but you do know, when you open a door in the winter, does cold go out or warmth go out? What happens? Does cold come in or warmth go out? Anybody know? Does cold come in or warmth go out? Yes, Harvey. Asked on mute. Hi, Harvey. Harvey, go for it.
Cold comes in.
Aha, Harvey! Sadly, a beautifully bold guess, but sadly not. The second law of thermodynamics says that heat goes from a place of high thermal energy to low thermal energy. Okay, high to low, which is why the sun, for example, all that energy is going from the sun out into space. Okay, so that's the second law of thermodynamics, and that underpins really nearly all of our particle theory, understanding of particle theory. Okay, cool. Right, let's go back to the experiments and see what's happened. Okay, so if we undo, look, I'm just going to bring back the detective iodine, look, and if I lift up the, oh my gosh, 3 of my very grubby fingerprints. Hopefully I can see, yes, I can see lots of little grubby fingerprints. Now, ladies and gentlemen, if you look closely, you can see, look, all the little ridges, very close up, all the little ridges of your actual fingerprints. And if you have your macro lens, you know, from your general kit, if you have your macro lens and actually look at that with your macro lens, you can see all the little ridges of your fingerprints. Now, believe it or not, the police and the crime fighters actually use iodine to do exactly this, to try and make visible fingerprints. So what's actually happening here in our little mug, a little cup here, is that iodine vapor is coming off, much like the vapor in a swimming pool, like the chlorine vapor in a swimming pool. It's coming up and it dissolves nicely in the fats of your fingerprints, okay? So the iodine is dissolving in the fats, and because it's so visible, okay, you can actually see it. So that's detective iodine. And if you want something here, look, a little thing you can do, okay, very gently, it's called a waft test, to smell a little bit of iodine. You'll see that it smells fairly similar to chlorine. What you do is you bring the cup to around about 5-10 centimeters from your nose, and just with the cup, you can smell the iodine. You should be able to bring that cup and you should be able to smell the iodine. It's kind of similar to chlorine smell. And Kelly, you stuck your nose in it. Don't stick your nose in it. It's fine. After saying, can you tour your room? Hi, Vance. My lab. You want to see the lab? Of course, right. It's the same one that's actually on the MEL science thing. So, right. So, let's go back to. Oh, look. Let's look at the reef. Has everybody seen the reef? Has everybody got this little beautiful reef pattern forming in their Petri dish? Yep. Cool. How nice is that? How pretty. A little tiny chemical reef should be forming. So what's actually happening there is a chemical reaction. The reef itself is a chemical reaction. And the potassium hexacyanoferrate is diffusing through the water, and it's meeting the copper sulfate crystals that are diffusing through the water. But they're not the whole chemical. They have dissolved in the water, so they are now ions, and the different ions are reacting. So in this case, we've actually got cyanoferrate ions and potassium ions and copper ions and sulfur ions all diffusing around, looking to see, hey, I like you better than the copper sulfate over here. So they react and they form a different compound, and you can see that forming right in the middle of that beautiful little reef. And the good news for ladies and gentlemen is you've got 2 more chemicals that you can test and experiment with yourselves. You've got 2 more chemicals you can explore and just see what kind of colors and reefs they do. So 2 more in your own time is sodium carbonate and iron alum. So there's 2 more chemicals there that you can do the same thing with, or maybe even add them to the same Petri dish and see what kind of reefs you can build with that. Okay, and then last but not least, look what's happened to our little bag. Look what's happened to our little bag. Can you see that some strange gunky blue substance appeared? Has some strange blue gunky substance appeared? Yes, I can definitely see it. The Simon Scott family, I can definitely see some gunky blue gunk. The Stotts, how are we doing, Stotts? Yes, you got gunk. Blue gunk is in the house. Avi, gunk. Kelly Schofield, gunk. We are properly gunked up. So what has happened here? Okay, so what's happened here is the iodine that's formed as a consequence of that reaction has got into the bag and gone, oi, I can get out of here. And it's got through the bag wall, the little tiny holes in the polymer. You didn't think that plastics had some holes in it, but they do. And iodine has shot through like a little piranha all over the place. And it's found the starch from your potato. It's found your starch from your potato and it's reacted with it to form, okay, it's reacted to form a compound, okay, which of course is black. And it's called a clathrate. And if I just show you this potato again, look. Can you see where I put the iodine on my potato? It's gone black. So I put this starch directly onto the potato and it's gone black. Okay. How cool is that? What a nice little bit of diffusion chemistry. Cool. Yeah, boy. Cool. So are there any questions? Are there any questions? Was that nice? Was that okay? Cool. Nice one. Thank you, Daniel. Thank you very much. Thank you so much. Stotts, got a question. Stotts. Go for it. Thanks, Vance. Thank you. Stotts.
Why does on the other side of the reef, why is one side clear and the other side blue?
Like, why don't they blend together? What keeps them from blending?
That's a lovely, lovely, lovely question. Fantastic. Right, when different compounds go into solution, some compounds are colourless. In fact, the majority, 90% of compounds that exist in nature are actually colourless. The potassium hexacyanoferrate, actually, when it dissociates, when it comes apart as a molecule, you know when you dissolve salt in water, everybody's done that, haven't they? Yeah? The salt, the white crystals, they just sort of disappear, don't they? They appear to disappear. Well, actually, what happens is the sodium and the chlorine come apart, and therefore you can't see them anymore. So those ions go into solution and form a colourless solution. Similar, the potassium hexacyanoferrate here, when the cyanoferrate and the potassium come apart, they form a colourless solution, but they're still there. They're still moving around. The copper sulfate, on the other hand, moves slightly slower. It's a different compounds, and molecules all move at different kind of speeds generally. And they're moving at a kind of similar speed to start with, but they form this barrier, this copper compound, copper cyanoferrate, okay, in the middle. And that's what that reef is largely made of. And once that reef forms, it acts as a bit of a barrier to the movement of the ions either side. Is that okay? Nice question. I like that. Very nice. Cool. Are there any other questions? No more questions? Aha, Daniel, go for it. Unmute. Unmute. Daniel speaking to Daniel. Go for it. Yes.
Are we going to do anything with the other half of the potato?
I suggest that if you haven't had lunch or dinner yet, that you wash your hands, peel it, and stick it in the fryer. just an idea. You're very welcome. So we're very welcome. Avi, hi Avi. Question asked to unmute.
What is the next class?
And the next class, thanks, McChristy. It's always handy. Avi, the next class is tomorrow. I'm doing the physics of vacuums tomorrow. So if you've got the vacuum set, I'm doing the physics of vacuum set tomorrow. And then if it's chemistry that you've got, the chemistry one is probably next week. But if you look on the MEL site, if you look at the subscription schedule, it'll tell you who and where and when all the different webinars are there. And I would love to see you, of course, back at that particular point. Okay, so that kind of brings us to an end of that little webinar. If you'd like a little postcard from me to say, yes, thank you very much, I want a little summary postcard of what we've done today. All you've got to do is put that little request into the chat, and we'll send, or to support@melscholar.com, or put it into the chat, or there's a sort of question there, and we will send you the card, a little personalised card, which is great. So good. In which case, thank you once again for subscribing to MEL Science. It's been really lovely to have you on board, and I look forward to seeing you again. Stay safe, stay well, and keep experimenting. And on that note, I'm going to say goodbye.